Science Beyond Borders. To officially start our activity, may we ask everyone to please stand up for a short invocation to be followed by the Philippine National Anthem. Let us all remember that we are in the holy presence of God, in the name of the Father, and of the Son, and of the Holy Spirit. Amen. Heavenly Father, we come to you with gratitude for bringing us together on this auspicious occasion. We thank you for blessing us with two esteemed professors who will share their life and work with us, and from whom we hope to learn great things. Therefore, Lord, we raise up this time to you for you to bless. May you grant us all wisdom and understanding and genuine learning to help us grow as scientists and as students and friends. All this we ask in Jesus' name we pray. Amen. In the name of the Father, and the Son, and of the Holy Spirit. You may now be seated. To officially welcome everyone, we would like to ask the Dean of the College of Science, Professor John Donny Ramos, Ph.D., to give his opening remarks. Let us give him a warm round of applause.
To our dear Honorary Professors, Professor Takashi Okamoto and Professor John Holdsworth, my dear colleagues, support staff, students, guests, and friends, a wonderful afternoon to everyone. Our celebration of Science Week 2017 is something very special because, of course, you know that we are celebrating our 90th year of foundation this academic year. This academic year, we are celebrating, therefore, 90 years of sustained excellence in science, education, and research. And of course, what makes this celebration extra special is because of the extra challenge we have to overcome before this activity because of the ongoing transport strike. But despite that strike, we are here, and no transport strike can prevent us from celebrating Science Week 2017. I'm so touched to see as many students this afternoon. Thank you so much for your sacrifice to come. And of course, our dear faculty members and support staff. We're moved by your support, and thank you so much from the bottom of our hearts. We celebrate Science Week 2017 around the theme, Science Beyond Borders, that is with the foresight that the practice of science should be inclusive in scope, responsive to global challenges, and should transcend artificial borders of nationality, society, ethnicity, and culture. Science should be a catalyst for change and should drive societal transformations. The practice of science should be pro-life It should be fair to the poor and protective of the environment. All these reminders should become our guiding principles in the practice of science. There is so much emphasis in the last few years on globalization, or some call it internationalization, including, of course, our very own academe. Internationalization has become a buzzword as well in the College of Science as we celebrate our 90th year of foundation. In the current academic year, for example, we have a number of activities that are international in flavor. They have been lined up, such as, for example, last December, the 3rd International Symposium in Molecular Sciences. And of course, last week, we have the ASEAN Universities Network, or AUN, Quality Assurance Assessment. We also have the international internships of our graduating students during the special term. And of course, this academic year, and that is this term, we have the enrollment of several Newton Fund Share inbound students, mostly coming from Myanmar. The hosting and organizing of lectures of the different number of foreign professors. The conferment, of course, this Science Week of our 3 honorary professors. And also, this week, we have the 2nd UST-USP, that's University of Shiga Prefecture, Joint Symposium on Environmental Sciences. Indeed, the UST College of Science embraced internationalization not because we don't have a choice, but because we believe it is the right thing to do to remain competitive, relevant, and a trusted educational brand in a global, borderless society. This is what we celebrate this week: Science Beyond Borders, exploring possibilities, solving global challenges. In this part of our Science Week celebration, we will listen and learn from 2 of our newly conferred honorary professors, Professor Takashi Okamoto for biology and Professor John Holdsworth for physics. I invite you, my dear students and faculty members, to listen, interact, and hopefully later initiate some collaborations with our speakers. Let us grab the opportunity to reflect on our role in doing deep work, as mentioned by Professor Cordell this morning. Before I end, of course, let me extend my earnest gratitude and warmest congratulations to the entire Science Week 2017 committee, led, of course, by Dr. Portia C. Quetulio, and to all the faculty members, support staff, and students, and of course, even our sponsors, for tirelessly contributing to the success of Science Week 2017, and of course, for making this week a galing science celebration. Magandang hapon sa inyong lahat.
Thank you very much, Dean Ramos. And to introduce our first professorial lecturer, in Honorary Professor in Biology, may we ask Associate Professor Mary Ann Santos, Ph.D., the Chairperson of the Department of Biological Sciences, in front.
It is my pleasure to introduce to you our speaker for the professorial lecture in biology. Dr. Takashi Okamoto was born on February 21, 1953 in Anjo City, Aichi, Japan. He obtained his medical degree from Keio University School of Medicine in 1977 and his Ph.D. in 1983 with his work on retroviral involvement in human autoimmunity. As a clinical associate, he specialized in clinical immunology of autoimmune diseases, such as systemic lupus, as well as of bacterial and viral infectious diseases. He was also the clinical chief of the infectious disease ward for tuberculosis. In 1983, he joined Dr. Robert Gallio at the National Cancer Institute, National Institutes of Health, Bethesda, Maryland, as a research fellow. Here, he published a series of seminal papers on HIV and human T lymphotropic virus type 1, or HTLV1, which causes adult T-cell leukemia. He was the first who proved that HIV-encoded TAT protein is the virus-specific transcriptional activator. On his return to Japan, he joined the National Cancer Center Research Institute in Tokyo, where he later became the section head of the Virology Division. Here, one of his pioneering works was the first mathematical proof of the multi-step carcinogenesis of adult T-cell leukemia, which received the Tamiya Prize in 1989. In 1993, he became professor and chairman of the Department of Molecular Genetics at Nagoya City University Medical School, where he directed a number of research projects involving the regulation of HIV transcription and on how autoimmunity is caused from the viewpoint of transcriptional regulation of pathogenic genes. His work on the transcriptional regulator nuclear factor kappa B brought him an academic prize from the Japanese Rheumatology Association in 2004. Dr. Okamoto has published over 200 original articles in international journals such as Cell, Science, Journal of Biological Chemistry, Immunity, and Lancet, among others. He has been an active member of the Science Council of Japan for a decade and has acted as chairman in a number of its subcommittees. He has also served as a medical advisor for the World Health Organization International Anti-Ebola Medical Team during an outbreak in Uganda in 2000. He first came to UST in the late 1990s through a collaboration with Dr. Gloria de Castro Bernas. And since then, he has come back on many occasions as a lecturer in various symposia and at one time as a visiting professor at UST Graduate School. He served as mentor to a number of Filipino graduate students, including two of our own faculty researchers. Because of his long association with UST, he was also instrumental in the forging of an MOU between UST and Nagoya City University. Ladies and gentlemen, may I present Dr. Takashi Okamoto.
Thank you very much for kind introduction. Good afternoon, everyone. I feel very honored to be conferred honorary professorship here in one of the most prestigious universities in Asia. Today, I would like to share with you some of our latest findings on HIV. I actually happened to find one editorial article in your UST newspaper this morning. And among the number of HIV-infected people here in the Philippines are already outnumbered that of Japan. So I think this is an urgent issue for all of us to consider a novel approach against HIV infection in order to help ourselves and save ourselves. And today, I would like to show you some of our latest data on our scientific explorations in seeking the genuine cure of AIDS and HIV infection, namely the inhibitors against HIV replication or transcription. This shows disclosure of my conflict of interest being none with regard to this presentation. And here you can see the epidemiology of HIV and AIDS. Worldwide, it is like plateaued after year 2000. And actually, the new infected HIV individuals were going down. However, if you look at the patients, patients under anti-HIV therapy, that means the patients necessary for the treatment became 8.2 million. And this is also because of the decreased cost of anti-HIV drugs, the dramatic decrease about $10,000 to 100 in only 16 years, okay? And in spite of this extensive therapy, number of AIDS-related deaths didn't change much. That there must be some serious problem there. Okay? So still, AIDS is number one killer as an infectious disease. And still increasing in Europe and the Pacific and especially East Asia. And as a matter of fact, the latest AIDS-related issue in the Philippines was documented in your newspaper, the Basitarian. It was February the 1st, see? I found it in my hotel, 1611. Okay. It says, no to condom distribution. The official website of Department of Health shows that between January 2011 and June 2016, over 8,000 HIV/AIDS cases of Filipinos aged 25 and below have been recorded. That is an enormous number of people. Department of Health has allocated 1 billion pesos for HIV/AIDS program, where 50 to 100 million pesos would go to condom procurement. And this is a cartoon. Oops. Okay. They believe, the editorial member believe, that this project by the health agency is not the best solution on stopping the HIV/AIDS cases. And proper education about responsible sex is what the youth needs. Department of Education should not be afraid to refuse in implementing such project and distributing those billions pesos to UST, I think. Hopefully they would say no and yes of redistribution. Okay. So why HIV is so virulent, as you just saw in the demographic numbers of increasing HIV-infected people among the the youth? Because it's rapidly spreading and killing the people. So what might be the secret of HIV in so doing? Retroviruses in general is not so quite pathogenic. And HIV is probably one of the exceptional cases. But if you see one exception, you will see another exception sooner or later. I will go into the details little later, probably in the end of this talk. So the answer of this question is in the action of viral proteins. Okay, if you look at the some clinical observations, that the higher the virus load is, the faster AIDS develops. So if you look at the number of CD4 T cells, immune competent cells in our bodies, when this cell number is low, like this, and the virus load is high. In 3 years, nearly 90% of these people become AIDS. In contrast, those people with very low amount of virus load in the blood and high number of CD4 T cells against HIV, almost none of them develop AIDS. So therefore, one of the goals is obvious, trying to reduce the number of viruses in the blood and thus preventing the killing of lymphocytes by the virus. That will be one of the answers to that question. Then, looking at the life cycle of this virus in the cells, starting from the left, the virus attaches to the cells, then the core of the virus particle will be integrated. During this process, DNA will be synthesized from viral genomic RNA. The DNA is in red, and this DNA will be further integrated into the genome of the cells. And as a form of proviral DNA, it stays forever, as long as the cells survive. Then, like your hemoglobin genes in the cells, it will endlessly produce the viruses, like hemoglobin is endlessly produced from your bone marrow cells. After the integration, and the provider DNA becomes a template for the next step of the viral production, that is transcription, followed by translation. And then the protein is synthesized, they automatically assembled and become a particle and start budding. And after the budding, the protein will be automatically degraded or processed, become mature viral particles that can be infected to the other cells of the same host. And the current therapy is called antiretroviral therapy, ART, is attacking reverse transcription step, DNA synthesis out of RNA. So because this is a reverse step of transcription, so it is called reverse transcription, okay? And then after the DNA is synthesized, it is integrated into the host genomic DNA. And this step is called integration. And there are two steps that can be targeted as therapy, for the therapy. And there are many effective therapeutic regimens so far. And then after budding of the viruses, the virus protein will be processed, as I just mentioned, and this was done by viral proteases. And the viral proteases are also the good target for therapy. So therefore, antiretroviral therapy targets three major steps of virus replication. However, as I just mentioned to you, even the combination of these life cycle inhibitors are not sufficient. So this is a pressing issues for HIV/AIDS epidemics. Number one, rapid emergence of drug-resistant viral clones. Genetic heterogeneity cannot be stopped by the current therapy. That is one major problem. Second, high incidence of serious side effects of the drug, so that people can not treat it for long period of time, over years. Okay, so they have to change the drugs. The presence of even drug-resistant clones, even before the treatment. In Japan, for example, 5 to 10% of the people newly infected of HIV virus already had the drug-resistant clones. So it could have been transmitted from the individuals under the treatment of the drugs. Okay? And then this number is dramatically increasing. And same thing is happening in this country as well. Therefore, current anti-HIV therapy is not sufficient, not only because of this, but also it cannot block the replication from the latently infected HIV. Okay? It's a latently infected HIV is generated from proviral DNA through normal gene expression step called transcription. There is no effective inhibitor against transcription. So therefore, the solution will be threefold. Number one, accumulation of epidemiological data and thorough analysis. I would say we need UNAs sponsored by WHO, like activity in the Philippine Department of Health. Number two, spread of effective information, probably from the Department of Health of the Philippines through social, cultural, and political activities. Thirdly, we really need to develop novel anti-HIV therapy with new concepts. And therefore, we need a specific finding for HIV research, both basic and clinical. So let's look at the life cycle of this virus again. Okay? As I just mentioned to you, the virus replication depends not on reverse transcription, because as far as the DNA is synthesized by virtue of reverse transcriptase, RNA is degraded because of the action of RNase H, which is also located in reverse transcriptase enzyme. So at most, one copy of DNA can be synthesized out of one copy of RNA. Then this DNA will be integrated. After the integration, like transcription of hemoglobin genes in our body, almost unlimited number of mRNA can be synthesized because DNA is double-stranded, and RNA transcription can occur from one of those strands, therefore preserving the other strand of DNA. Okay. And to make things worse, the virus can stay as the DNA as a latent form of infection. And the transcription takes place from this DNA, and the amplification of HIV-1 genetic information can be achieved only at the step of this transcription process. And thus, drug-resistant viral clones can be generated with a background of heterogeneity due to dramatic genetic amplifications. It is not unfair if we attack the weak point of the virus, okay? In judo, it is considered not a good idea to attack the weak point, to be fair. But because the HIV virus itself is not fair, it is not unfair if we attack the weak point of the virus. So let's find the weak point of this virus and attack them. In 1986, as early as 1986, we have published in Cell, long time ago, when I was still 30 years old, we demonstrated the first evidence that HIV is amplified at the step of transcription using in vitro cell-freeze analysis, and we found TAT is responsible. TAT protein is responsible for this action. And later on, we have consolidated the evidence. So this is a cartoon representation of what we have found. Here is viral messenger RNA with TAR RNA, we call it stem, bulge, and loop structure. We should have patented this from NIH, but it's too late because we have already published a long time ago. And it is this structure that TAT specifically binds. Okay? Not only TAT, but also cell transcription factor called PTFB, consisting of cyclin T1. It's a direct interacting molecule carrying cyclin-dependent kinase CDK9. The importance, significance of binding or recruiting PTFB to TAT and TAR RNA, meaning the viral mRNA, is the following. Since PTFB carries a CDK9 enzyme, it will, perhaps there is some problem, but this CDK9 will phosphorylate RNA polymerase 2 at C-terminal domain called CTD, thus making this polymerase to be more processive so that HIV transcription can accomplish its mission. So in order to block this action of TAT, we really need to know the molecular and structural details of this interaction between TAT and cyclin T1. Okay? If we are able to block this process by finding a new compound that can block this process, so-called TAT inhibitors, it should inhibit not only viral replication, thus preventing AIDS development, but also emerging drug resistance. Thus, the conventional anti-HIV therapy can still work for years. That is not the entire story. There is another story that we have found in 2000 year. TAT also induces by itself immune deficiency. This study was done by Dr. Saror from UP Manila, when she was staying with us. We have looked at the affinity between cyclin T1 and TAT, which was very, very strong. And TAT is not only the target of cyclin T1. There are many other cellular transcription factors that can bind to cyclin T1, like C2TA. C2TA is class 2 MHC transactivator and responsible for the gene expression of many genes for immune responses, specifically against the viruses or against the cancers. And both TAT and C2TA is recognized by cyclin T1. However, the affinity of TAT to cyclin T1 is much stronger than that of C2TA. Thus, most of the cellular cyclin T1 will be recruited to HIV transactivator TAT. Thus, MSC expression is suppressed, thus suppressing the antigen presenting cell function, as well as augmentation, dramatic augmentation of HIV transcription. Thus, immunodeficiency is further augmented. However, so we call it the triangular relationships at the molecular level among TAT, cyclin T1, and C2TA. So probably TAT is probably more attractive than C2TA from the viewpoint of cyclin T1. It's like a boyfriend and girlfriend situations. I think many of you know. Okay, so what can be the clue? So what about blocking this unwanted interaction between cyclin T1 and TAT? And then it should restore the normal friendship between cyclin T1 and C2TA. So everyone will become happy. Therefore, the TAT inhibitors should effectively inhibit HIV viral replication, prevent the emergence of novel HIV clones that are resistant to conventional anti-HIV drugs and host immune responses. The reason I mentioned this is because at the transcriptional step, there are a number of polymorphic HIV clones generated. Because transcription, augmented transcription, does not seem to have error prone. So therefore, the accumulation of mutations are taking place during the TAT-mediated gene amplification. And that would be the background for drug resistance. As I mentioned in the previous slide, the TAT inhibitors should restore the production of MHC class II proteins and thus restore the immune responses. This is an old Chinese saying, know yourself as well as your enemy. So let's know TAT and PTFB in order to molecular design a TAT inhibitor. So this one was actually from the published data by Tahirov in the United States, in David Price's laboratory in the Midwest of the United States, published 2010 in Nature. We have been actually looking for collaborators of crystallography, but they actually scooped us. They did a crystallization of the TAT protein complex in order to see the exact geographical locations of TAT in relation to cyclin T1 and CDK9. Okay? This is a crystallographic analysis of the TAT cyclin T1 CDK9 complex that is a core of the secret of HIV replication. Let's look at this cyclin T1 TAT interaction more carefully by expanding and changing the representation, ribbon, and also the wire, ball and stick models. As you can see, between the TAT in purple, and cyclin T1 in blue, there are a number of places where the interaction, atomic interactions are taking place. I think Dr. Holdsworth and my colleague professors know much better, but I can just show you that there are some critical amino acid residues that are core to this interaction. So this is actually the solid model of the crystallographic structure of the protein complex. And there is another one, asparagine 60 on cyclin T1, that acts as a node of H2 and H1 dash and H2 dash helical interactions. And as a matter of fact, by simple substitution of this single amino acid could reduce the action of TAT dramatically, as you can see here in solid lines. Okay? It suggesting that there might be some allosteric effect that we might be missing here. And then we initiated in silico drug screening with a concave structure of cyclin T1 that was predicted from the crystallography. Okay. Here is a cyclin T1, and here is a concave structure within the cyclin T1 for the TAT to bind. Okay. So we call it the TAT ballet. TAT actually binds here, and we confirmed this direct binding by making a single amino acid substitutions and published in Journal of Molecular Biology in 2011, 6 years ago. Okay. So then we now confirmed where the TAT binds to it. Okay. Then we, according to the normal scheme of drug development, we have applied in silico screening, drug screening, against this particular concave structure on cyclin T1. We found significant but not very strong inhibitory action using the cell system, and which is specific because this compound did not have any effect on anti-NF-kappa B action, which is another transcription factor. However, TAT activity was dramatically and significantly reduced, but at very high concentrations. But this kind of compound has never been published because it also acts on chronic HIV infection. Chronic HIV infection depends on transcription and the gene expression level. Only the transcription is affected, so that TAT is now shown to be inhibited. TAT is not almighty, it's not the strongest, judo player. It has a weak point, and this is a weak point, okay? And the latent infection can be also blocked. But the problem is a very high concentration of these compounds, although it doesn't have any side effects so far, okay? However, in order to make it as a drug, chemicals, we need more fine-tuned structural validations. So, however, the inhibitory action was not strong, though specific enough to persuade chemists of pharmaceutical companies to start the synthesis of chemical derivatives, one of which should be more effective and could be a candidate for the drug. Novel drug. So we had retracted the patent application in accordance with the suggestion by the specialists at JST, a Japanese source for the intellectual property affiliated with the government. Since the three-dimensional data obtained by X-ray crystallography is considered just a snapshot of flexible protein complex, we have adopted molecular dynamics MD simulation to look for the better matched inhibitor compound. So this is just a principle of molecular dynamics simulation. Perhaps you can find a better explanation in a textbook, so because of time I can skip this. And however, using this, we were able to make a simulation of this cyclin T1 molecule, which was taken, isolated from the three molecular complex in the first place. And this one was published in PLOS One 2 years ago by Asamitsu in my laboratory. And this shows the flexibility of this cyclin T1 protein can be inhibited by making single amino acid substitutions in those amino acids positions that are critically involved in the protein-protein interaction with TAT. Okay? And we are now using supercomputer for analysis of tri-molecular complex. And this is one of the data that we have in press in PROS 1. MD calculation has revealed with the 3 molecular complex a new finding. The TAT binding to cyclin T1 actually exposes the catalytic signature sequence called the pitallure to the solvent, the water, okay, here. And the catalytic center, this is quite a new finding. As you can see here, the cavity appears to be a little bit expanded. And as a matter of fact, when we look at the cavity, see, this one is without TAT, okay? The cavity initially appeared to be separated by pitallure sequence. However, when TAT is present, this cavity becomes continuous, okay? So there is a very good candidate cavity for the drug development. And currently, we are screening in silico against 3 million or 4 million, whatever, compounds, and we have already identified nearly 100 candidate anti-CDK9 inhibitors. And their anti-HIV activities are now underway, okay? And the next paper, we will show the identity of such compounds. So by using a novel method, floppy system, we are now able to visualize the TAT cyclin T1 and CDK9 trimolecular interactions in live cells. And this floppy system is called the Fluorescent Detection System of PPI, recently developed by Dr. Miyawaki of Riken Institute in Japan. We are able to use this system and developed a novel method of the detection of protein-protein interaction in live cells. And when protein and protein, in this case, TAT and cyclin T1 taking place, then we can see the location of this interaction as a clear green dot, as you can see here, like this. So it happens in the nucleus as well as in the cytoplasm. And addition of CDK9 further amplified the intensity of this foci, suggesting that CDK9 stabilizes the TAT cyclin T1 molecular complex. So therefore, that is the reason why trimolecular complex is necessary for full action of HIV. Okay. Interestingly, this identification of basic molecular event can also be applied to other related but distinct biological phenomena. Elucidation of TAT action revealed novel aspects of regulatory mode of gene expression, especially the generation or emergence of new catalytic cavity within CDK9 molecule. And the expression of most cancer or leukemia-related genes are regulated at the transcriptional elongation. And this is called the promoter proximal posing, PPP, okay? And if we can control PPP efficiently as at our will, then we can also treat the cancer or leukemia. And interestingly, we found the cyclin T1 molecule interacts with a number of transcription factors, not just TAT and C2TA, but also other transcription factors such as c-MYC, oncogene protein, or NF-kappa B, that is also pro-oncogenic protein, through naturally denatured region of cyclin T1 protein. And since this is a naturally denatured region, it is very difficult to predict the structure. Therefore, it is not easy to design a drug. So this kind of bioinformatic analysis is essential for finding and identifying effective inhibitors. Okay, this is the last slide, Science Beyond the Borders, as Professor Lams just mentioned. So we really need some collaboration amongst not only between Japan and the Philippines, but also Australia, United States, Britain, and other countries, and with UST as a convergence point of such discussion. And lastly, I would like to thank my collaborators, namely Kaori Asamitsu, Yorina Hibi, and Miyuki Sakai. And also I would like to make special thanks to Professor Takatsugi Hirokawa, who is an expert of the computational analysis of proteins. Okay, these are the pictures of these people. Thank you very much for your attention. I'm happy to take any questions.
Thank you, Professor Okamoto, for that very enlightening lecture. We will have the open forum after both of our honorary professors have delivered their lectures. At this juncture, to introduce our next honorary professor who will give a lecture, let's call upon the chairman of the Department of Math and Physics, Engineer Enrico Yambao.
It is my honor to introduce to you one of our honorary professors for his professorial lecture in applied physics. Dr. John L. Holdsworth obtained his doctorate degree in chemical physics from Griffith University, Australia in 1996. Currently, he is a Level C Senior Lecturer of Physics in the School of Mathematical and Physical Sciences, Faculty of Science and Information Technology, University of Newcastle, Australia. He was the Assistant Dean, Faculty of Science and Information Technology, also University of Newcastle, Australia, and was the Chairman of the Department of Physics at the Ateneo de Manila University from 1999 to 2001, where he taught physics from 1995 to 2001. Dr. Holdsworth was awarded the University of Newcastle Vice Chancellor's Award for Teaching Excellence in 2005. He has authored and co-authored a total of 28 articles published in reputable journals like British Journal of Dermatology, Journal of Chemical Physics, Optic Letters, and Journal of Non-Crystalline Solids, just to name a few. He has presented scientific papers in both local and international conferences of prestigious organizations like International Society for Optics and Photonics, American Institute of Physics, and Institute of Electrical and Electronic Engineers, and has been working with 29 local and international research collaborators. His research interests include photonics, material science, and chemical physics. Dr. Holdsworth is a member of different international professional organizations like the International Society for Optics and Photonics, Institute of Physics, Australian Institute of Physics, and the Australian Optical Society, as well as the Optical Society of America. Dr. Holdsworth was instrumental and played a significant role in the development of the BS Applied Physics Major in Instrumentation program in our college that led to its offering in 2002. He handled the general physics of BS Biology Accelerated Class, gratis con amore, in the academic year 1999-2000 in our college. And just like each of you, Dr. Holdsworth also experienced the floodwaters in our campus. There was a time in which He attended this class totally barefooted because of the flood waters in our campus and its vicinity. He has given lectures on several occasions in UST, such as the reference Father Ciriaco Pedrosa OP Memorial Lecture in Mathematics and Physics, the alternative class during Science Week 2014, and Science and Technology in Education on February 6, 2014, in cooperation with the College of Engineering. He supervised 2 students in 2014 and 1 student in 2015, all enrolled in BS Applied Physics program of UST in the research internship in the University of Newcastle. So without further ado, may I call on Professor John L. Holdsworth for his professorial lecture in physics entitled Lights and Interactions.
Sound. Thank you, Engineer Yambo, for that introduction. And it is a delight to be here. And I am supremely honored by your presence here today, students. I can say that if you were in Australia, you'd be at the beach. The fact that you're not in a mall and here is a great honor. So thank you. So I would like to explore some light and interactions, and these things shape our existence. So within the talk today, I would like to pay homage to those that have gone before, both the observers of light and the theoreticians, because they have provided the framework that we build on today. And they are the giants on whose shoulders we stand. I'd like to look at how you can make light, how does light interact, how you can finesse light. And in fact, in the last lecture, we saw some brilliantly finessed light that is used in the measurement of the proteins. What can you use it for? And then some of the work that I'm doing at present, light and the environment and light in human tissue, and then to conclude. So we are fortunate. We have our own personal nuclear fusion reactor. It is 8 light minutes away from us, and this allows life on Earth as we know it. We are in a Goldilocks situation. We are not too hot, not too cold. We are just right. And NASA just announced the discovery of another star with 7 planets, I believe 3 of which are just right, we think. So our particular nuclear fusion reactor provides for us all that we need, really, and life and light go hand in hand. So Newton, I should start with the Greeks, because everything started with the Greeks. Scholarship started with the Greeks, the study of things. And Ptolemy actually wrote about optics. And then many years later, we have Isaac Newton, 1665. His principal work on optics, but do you know he took that prism and he took a shaft of sunlight coming from our own personal nuclear fusion reactor and he broke it into colours. And then he used another prism and put those colours back together, therefore proving that sunlight was made up of different colours. It wasn't the prism that was colouring the light, it was the light that provided the colour. Now, we all know about this red orange, yellow, green, blue, indigo, and violet. Herschel, the fabulous astronomer, realized in 1800 that heat was perceptible as near-infrared light in this zone here. And that followed soon after. Ritter in Germany identified the ultraviolet, which inhabits this area here. It followed in 1881. Note those years. They're not actually that long ago. While you might think that I'm impossibly old and, a century is just, an age, in scientific terms and in the life of the planet, it's not. Oops. James Clerk Maxwell. Students of physics will love this. Students of math will love the differential and integral forms of Maxwell's equations. They make your head hurt just looking at them. But they are solvable. And, in 1865, James Clerk Maxwell compiled these and wrote them in these forms, and he provided the solution. And that solution is both wonderfully simple, deeply insightful, and they could not argue with it at all, because it was a wave traveled at the speed of light, and that speed was predicted by Maxwell to be this. The speed of light in vacuum is the inverse square root of the permeability and the permittivity of free space. And those, so far as we know, are fundamental constants of nature. So, from some arcane mathematics that I know students of physics love, these mathematical equations comes an insight that gives us a fundamental truth, the speed of light. Now, I've got approximately 3 by 10 to the 8 meters per second. It is defined by international standards to be very close to that, not exactly that. And we know from measurement, from observation, that when we are in a media, this speed is reduced, and it's reduced by a factor. That factor we call the Index of Refraction. If you are a chemist with a liquid chromatography apparatus, or a biologist who's using one of those, you will use a refractive index detector. So the study of light and its measurement is now embedded in the instrumentation that we take for granted. This solution is, of course, a sinusoidal relationship, and it carries energy in this direction, in the direction of the motion of the wave. And while that's a beautifully simple picture there, it's also false. But that great insight allowed us to imagine and quantify the entire electromagnetic spectrum. And this is something that you use all of the time. We all walk around with one of these in our pocket now. This is possible because of the insight of Maxwell. The selfies that you took with me on the stage before are possible because of the insight of Maxwell. Because what we're looking at is the electromagnetic spectrum. And it's only this tiny, tiny, tiny bit of it, between 400 nanometers and 750 nanometers, that we can see. The rest is, we label as ultraviolet, going down shorter, and below ultraviolet we have our X-rays that we use, of course, for medicine and for scientific endeavors. Going the other way, we have infrared light. And I noticed some posters using the Fourier transform infrared spectrometer. So it's using light that exists in this wavelength range here. Or expanded, it's this wavelength range here. Microwaves you use to cook. We use to communicate. When we're dealing with communications, if you've got time, you can watch TV because of the electromagnetic spectrum. Now, in 1900, this was, or in the years just before 1900, this was a very, very rich environment for physics. They thought they almost had things sorted. And what we are about to embark upon is some thermodynamics. Now, if you didn't like math, I know that you're not going to like thermodynamics. But thermodynamics and the study of thermodynamics actually looks at where energy goes. And energy drives most things. So here I've got a picture of lava, and we will return to that a little later. And what I also have here is the equation that gives how much heat per unit time, how much energy per unit time is radiated from that material, that hot material. It's proportional to temperature in Kelvin. I'll say that again with emphasis. The temperature in Kelvin raised to the 4th power. Now, your temperature in Kelvin is roughly 300 degrees. Raise that to the 4th power, and that's how much energy you're radiating. Now, this was known, the measurement of how much radiation came out, that comes out in proportional to temperature was known. This is known as Blackbody Radiation. And Stefan Wien's law is this relationship between the temperature and this peak wavelength here. Now, Rayleigh and Jean weighed in, and they had an equation for this. But that equation here was incorrect. It predicted an ultraviolet catastrophe, and it took Planck, actually for the wrong reasons, to correct it. And he found the relationship here that gives exactly, if you plot this relationship, you get precisely the blackbody radiation. And in doing so, he had to introduce a constant, Planck's constant, and sort of by accident, he had to quantize energy. And it took Einstein and his great genius to name a photon and to identify that a photon had a packet of energy that was proportional to the frequency of the light. And this was his seminal work of 1905. I know you think I'm impossibly old and a century is just such a long time, but that's not that long ago, really. And we're still coping with that. So here we've got this picture from Maxwell of this wave nature of light, and this is incontrovertible. Light travels at the speed of light, and you can calculate what that, I beg your pardon. You can calculate what that is from this expression here. And we have Einstein saying that there's a photon that has a wave packet that is proportional to the frequency of this wave. And how do we bring those two together? Well, we still puzzle over that. There is the wave-particle duality of light, and to this day, photons exist only in two states, either right circularly polarized or left circularly polarized. Many of you in your experiments and your instruments used linearly polarized light, which means there's an equal number of right and left circularly polarized photons. How do they know? I have no answer for you. And Einstein himself was greatly puzzled about the nature of a photon. And photons carry spin angular momentum, and that is a relatively new understanding. So, fluorescence of materials. We can identify materials by their spectral emission, and this is a fingerprint of the particular atom, and we can tell precisely about that atom. This is hydrogen spectrum here. By measuring this very precisely, we can identify the element. By measuring these spacings between them in frequency, this becomes a characteristic fingerprint. Students of physics will know about the Doppler shift. It's called the cat law. Meow. So things that are coming towards you are a higher frequency, and those that are going away are of a lower frequency. It's the same with light. So by measuring the frequency and the separation between the lines that come to us from starlight, we know precisely what is in the star, and we can tell if that star is moving away from us, moving towards us. If we look carefully at that star, we can measure the light coming from the side that is moving towards us and the side that is moving away, so we can measure the rotation of that star. Now, we'll return to our thermodynamics, and we've got this area of the object, and the temperature of the object gives the amount of heat that is radiated. We can identify processes, and Einstein gave us this one here. So there's stimulated absorption, where a photon comes in and an atom changes energy state, moving upwards, and then it can relax down by the emission of a photon. But there's another way, and that requires another photon be present, and that will stimulate the emission, and we have an exact twin that comes out with that. So this process here, or these processes here, must match these processes here. And this process here gives the radiance of an object. Mary, if I look at you, I can say, you are radiant. That comes because she has a temperature that's above 0 Kelvin. And then I'm radiant. The chairs are radiant. The walls are radiant. So we live in this bath of radiation, and our net energy transfer comes from the difference between the radiation going out and the radiation coming in. So we return to lava, and how do you make light? So I've already given away that that is lava. How do we know that that is hot? It's red. It's red. It is so hot that its emission is in the visible domain and red light. We know that this little bit here is hotter than that little bit because this is a brighter shade of yellow versus this being a deep red here. And this process by which hot things give off light is called incandescence, and both Swan in the UK and Edison in the US made these things, and they made them in 1880. Now, I know you think that that's an impossibly long time ago and I'm ancient, but it's not that long ago. Fluorescence we've discussed. We can make fluorescence if we have electron impact, and this is 579, 577. This is a sodium emission line here, or lines, and so it's characteristic of sodium under electron impact, or we can excite optically. In the modern age, we can make different size particles, and they will fluoresce different colors because of their size. And these are cadmium, selenium, quantum dots that are in solution, and they have different colors depending upon their size. But this is fluorescence, and I noted that the images of the TAT protein, the blue-green fluorescence, is in fact this process. Now, phosphorescence is what we are used to in our watch, and this repeating GIF here shows different compounds that retain their emission with time, and it slowly goes dimmer. And that comes about because this transition here from a triplet state down to a singlet state is forbidden. If your parents forbade you to do something, do you still do it? Yes. Do you do it frequently? No. So phosphorescence is exactly the same. It happens, but slowly. It happens infrequently. And then chemiluminescence, we all do this at party time. Mix two chemicals together, peroxide and a phenyl oxalate ester, which ultimately gives the glow stick light. And then the modern one, electroluminescence. This has really, really taken off since the invention of the LED, and most of the development of that has gone on since 1960. And you note that these have bandwidths that are quite wide. So there'll be 20 or even 100 nanometers bandwidth of this blue LED here, and we see red and green. And when we combine these three together, of course, we can get white light, and you young people know all about 4K displays for your gaming that are LED-based devices. A white light LED is in fact a UV emitting or a deep blue emitting LED with phosphors around it. So this is the structure of a white light LED. Now, Bremsstrahlung. Bremsstrahlung comes from a German word, means breaking light. If you accelerate an electron, it will emit light. So if you have a synchrotron where you're spinning electrons around a very large circle, but each point on that circumference, the light comes out tangentially to that because as you know about going in a circle, it's centripetal acceleration, so the light is emitted perpendicular to that. Or X-rays. X-rays, if we accelerate an electron with 100,000 volts and slam it into a piece of copper and tungsten, we get X-rays, and that is the source for our medical X-rays. Cherenkov radiation, I hope you never get to see this. This happens on the inside of a nuclear reactor, and it occurs because muons are going faster than the local phase velocity of light. If a bullet is fired, the gun goes bang, of course, it makes a noise, and then you've got this slug of metal which is whizzing out, it flies out. It doesn't have a speaker on it that says, I'm coming, but it makes a noise. And it makes a noise because it's traveling through the medium of air faster than the speed of sound. So that is the source of its sound, and it's, by analogy, it's the same with the muon here. When it's going faster in the water here than the local speed of light, it emits light. So thus we come to all of the sources of light. That's it, people. That's the only way you can generate light. And how does light interact? It only does four things. It reflects, it's absorbed, it's transmitted, or it is scattered. And reflection we see briefly when we look at ourselves in the mirror in the morning, or perhaps for a prolonged period of time. When we look at anything, we see it because of the light reflected off it. In this case, our personal nuclear fusion reactor that's up in the sky is providing the light that is reflecting off this structure and then reflecting off the water into our eye. So we observe this. We can either get a specular reflection or it can be diffuse. You're seeing me because of a diffuse reflection from me. Absorption, where the energy goes into the material and is retained in the material, so the amplitude of the electric field decreases, and we use this all of the time with color filters to block particular regions of the spectrum and generate our little disco ball whenever we're in a party mood. Transmission, light goes straight through. While it's inside something, its wavelength is shortened, but its frequency is not. And this light here is transmitted through this block. The last one is scatter. And this actually, for my work later, turns out to be very important, and it's perhaps the most difficult to deal with. If we've got pure water and we're putting a laser through it, that laser will go straight through. If we've just got 1 cc of milk mixed into this, the fat globules in the milk scatter the light and very, very little gets through. If we put 4 cc of milk, this is almost totally scattered and nothing observable gets through. Now, it's elastic scatter that gives our blue sky, seeing during daylight, and then scatter from light and dust and other aerosols. It scatters light proportional to the wavelength. And I'm sure that we've all seen a deep red sunset. Wait a minute, you live in Manila. Every sunset is deep red because of the particulate material in the atmosphere. Now, what usually happens? Well, everything happens all at once. And this is a piece of beach that I hope you get to visit once in your life. This is Whitehaven Beach, close to the Barrier Reef in Queensland. And you see this. You see the blue of the sky, the white clouds are because of me scattering of the light from the water droplets. The water is green here because of Raman scatter, makes the sea look green, and you can see the whole thing because of reflection coming off it. So, this personal nuclear fusion reactor that we have provides us heat, light, that comes through the atmosphere. It provides us ultraviolet, which will give you a suntan. We are prevented from being roasted and toasted by ozone that is in the stratosphere. And we're prevented by Rayleigh scattering because this is proportional to the inverse quad of the wavelength. This happens predominantly in the ultraviolet and less so at the longer wavelengths. So if you're on a mountaintop, you have to worry about UV because Rayleigh scattering is reduced. This is the light that comes down, and it's transmitted through this region of the spectrum. So this red curve here with its little dips, that's what comes down and heats our planet. Because hot objects radiate, Depending upon the temperature, you'll have a range of spectra, and the Earth radiates back out into space. If you were in a desert where there's very little water, it gets very cold because you get this excellent radiative cooling of the Earth where there's very little water. And you can see the molecular components of the atmosphere and their absorption spectra. Why do people worry about carbon dioxide? Because it blocks this outgoing radiation, and the carbon dioxide will retain energy within its molecule. The other major greenhouse gas, methane is worthy of interest because it will block this zone here, but the principal one is actually water. Now, water does, of course, condense and will fall out as rain, but there's a lot more water now in the atmosphere than there used to be. How do you finesse light? Well, you make a laser, and for students of physics, tomorrow we'll talk more about lasers and applications. Now, in order to do that, in order to make a laser, we make use of this process here, the stimulated emission process, and we need to finesse the system because Maxwell-Boltzmann statistics will tell us that most of any ensemble of systems is going to be in the ground energy state, very, very little in the excited state. We need to invert that. We need to get a greater number up in an excited state and fewer down here. So we drive that very far from equilibrium. And how do we do that? We choose a phosphorescent atom. That one that wasn't behaving itself, breaking the laws, but doing so slowly, that allows us to couple energy into a state so we can excite up here, and there's a very fast relaxation of energy down. We populate an energy level of the atom, and there's slow relaxation here. This is very fast, but we have this inverted population, so stimulated emission can occur. And then we need to put some mirrors around it. When we do that, we generate a laser beam coming out. And when we've got a laser beam, it's nice and collimated. I have a laser pointer. This one cheats a little because it's got a lens in front of it, but it's collimated. It's monochromatic. My little laser pointer here is green. It's not white. Okay, it doesn't have all of the colors. It just has green. It is coherent. You might be able to see if I can hold it still enough that it looks sort of speckly. That comes because of the coherence of the beam. And they can be pulsed or continuous. They can also be tiny, small, large, or just plain enormous. The biggest one on the planet is a national ignition facility in the US. There are 192 beams that all converge on a tiny, tiny little hollow realm. And on the inside of that, there's a glass pellet, about 3 millimeters diameter, that has helium-3 inside it, or tritium. And this energy coming in here will generate a bath of X-rays, which compresses that and achieves nuclear fusion on the planet. Now, fortunately, we have a nuclear fusion reactor that is 8 light minutes away from us, because this one only works once every 3 hours, and then you need to put more energy in than you get out. Its power, its peak power, is 500 petawatts. Now, if we forget what a peta is, we have kilo, mega, giga. I've forgotten the next one. And we're going up to 500 by 10 to the 12 watts. So we've got 500 petawatts of radiant energy. The world's smallest laser looks like that. Its active element is about a grain of salt. It's very tiny. And what do we use them for? Mostly, we use them to watch Buffy the Vampire Slayer. DVDs, Blu-rays now. The blue wavelength has shorter wavelength. We can focus it smaller. We can get 25 gigabytes on a disc that is the same size as a CD, and a CD would only take 700 megabytes, and it's a longer wavelength. We can also take those diode lasers and we can pump other lasers, and this is a laser that is built inside a piece of optical fiber. And it couples fairly messy light that comes out of a diode laser into very, very nice light that comes out of a fiber laser. And you can combine these fiber lasers, you can stack them up and combine them so that you can generate a very large high power laser which you can use to cut. And I'll have more to say about this tomorrow. You can make a figure-of-8 laser, and this laser was made by Crystal Colandrino, who was a UST scholar in my lab. And she learned how to splice fiber together and indeed make her own personal laser. Now, light and the environment. This is work that I've done for many, many years, and particularly this started at the Ateneo. And my colleague there, Manila Alarcon, established the system. Susana Dorado did her Ph.D, and Genelita Tobal did her Ph.D on the system, and Nofel Lagrosas completed his Ph.D in Japan, but also was instrumental in this work. So if you take a laser, a pulsed laser, and you expand it so that it's a nice beam going up, when it goes up into there, it's going to interact with the dust that's there. And light interacts by reflection, absorption, transmission, and scatter. In our case, it's going to backscatter via me scattering, and so we then have some signal coming back from the clouds here that we can detect in a telescope and a detector. An oscilloscope is a time-based thing, so we just measure the time between when the laser goes up and when the light comes back, and that will tell us how far away this is here, so we can range clouds and dust in the atmosphere. This shows the Manila Observatory, where this was based, and this is in the grounds of the Ateneo. You might notice here that there's a beam of light going up. If the air is clear, you can't see it. So because you can see it so clearly, you know that there's a problem with Manila atmosphere. So this is, you can really measure, and we did measure, if you like, the scatter from aerosol pollutants that takes place. And yes, we got up at 4:30 in the morning for this one, and then we ran it pretty much all day. These are nocturnal layers of the atmosphere, and they exist at night. Those of you who have lived down in Marikina Valley would see river mist at night, and this is what this looks like when you measure it with a laser. And those temperature inversions exist in the atmosphere. The sun comes up, and then that drives this whole process here, this convective upwelling. So the highest concentration of pollutants is when everybody is just heading off on their jeepney ride. Obviously not today, but when they're all hopping in those jeepneys with the modern pollution-filtered engine, or not, and the smoke belching that comes out of that really loads the atmosphere with a high number of high concentration of particulates, and this is what the laser measures. And we can see that this goes up. This is characteristic behavior of the atmosphere. As it lifts up during the day, there's capping inversion, and then that whole cycle begins again the next day. So, you know, there's a whole lot of pollution happening down around the 500-meter level, which ultimately is what you breathe, which is a bit sad. Now, I've continued that work in Australia, and this is some work I did with CSIRO and my colleagues Howard Bridgman, Matthew Pickett, and my student Tony Leckie. We set up a small LiDAR system that was just at the back of this building here, and what we were measuring was the loading from coal mining activities. And this is a coal a blast, and this is a drag line here that is scooping up the overburden. And both of these things affect the environment, of course. So we could measure, and this was the first time this was ever measured as far as I was aware, the vertical extent of a dragline dust plume. And this then extends about 300 meters up into the air. Previously, all of the measurements were done at ground level, and they had no information about the extent of the vertical plume. And, you know, we do need to be able to measure that. This is some work from August last year, and this is my hometown, my current hometown of Newcastle. It is the largest coal export port in the world. 160 million tons of coal is exported. Now, all of that is burnt. Not necessarily in Australia, so we have clean air, but somebody else doesn't. And there are coal loading facilities back here, and they give us dust, but this little LiDAR system is measuring that. This is another system that I'm associated with Rio Tinto, who mine iron ore, and this is the environmental monitoring at Cape Lambert. And you can detect here a plume of dust which is coming from the the iron ore loading facility that is there. So we can use these LiDAR systems to monitor the environment. What I'm working on with students at present is making a fast scanning LiDAR so that we can monitor this sort of blast plume. So this is where it started, or, you know, when I heard it and then ran and got the camera, and you can see this plume extend, and my last photo before I lost visibility of it is here. This plume contains lung-damaging dust, and what we want to be able to measure is where that goes. Now, this is not my work, but you should know that there are LiDAR systems in space, and they circulate around the globe, and they can measure They can measure the pollution, the smoke that is coming off the Indonesian and Malaysian forests that are burning, or the forest in Brazil, or when my country, as it's wont to do, goes up in flames, that smoke goes well up into the stratosphere. And this affects the albedo of the Earth, and so NASA want to measure that. So there's a series of satellites which are in orbit, and the Calliope LiDAR is one of those. Equally, NASA, together with the Oceanography Institute, have seaborne LiDAR systems. They also have airborne LiDAR systems, and these will measure the growth of phytoplankton, and if there's a school of fish underneath them, they'll also measure the presence of fish. Now, that brings me to what I really want to talk about, which is light in human tissue, and this is something that I have done pretty much since I was your age, or a little bit older. And I know I'm impossibly old, but it's not that long ago. So this is a gold vapor laser, and this is a copper vapor laser. So as the name suggests, these are metals, and if you heat them up enough and you put 30,000 volts across them, they will give you green and yellow emission and red emission here. Now, why is that interesting? Oh, this is the next prototype after those ones I couldn't take out of the laboratory. This is the first prototype that was down in the hospital, and I've got some optical fibers here. And we use this to treat patients with cancer phototherapy. That was the second edition. It looked rather nicer, and you might recognize that person from a long time ago. That is the yellow light of copper, which gets used for birthmarks, for port wine stains. I didn't have a port wine stain, but we just needed a patient for the photograph. So, light in human tissue. Hemoglobin, which is this red curve here, has two peaks. One is in the green and one is in the yellow. And this yellow one is oxygenated hemoglobin, and which is why the yellow light was used to couple energy in here. The red light for cancer phototherapy, you want that to penetrate into the tissue. So you want to move away from the absorption of hemoglobin, and then you see this absorption takes a dip here. So moving to about 650 nanometers gives you much greater penetration in tissue. This blue curve here is water absorption, and we've got the oxy and deoxygenated hemoglobin and melanin. So melanin, as you're aware, is in the skin. You can go subcutaneous if you use a needle, but you can also get light through tissue. So this region here allows the greatest penetration into human tissue. Now, I've had a bunch of students work on this, including Marvin Gabriel and Ivan Lazate, who are both scholars from UST. My colleague Galia, who was a former Ph.D. and is now a colleague. Elham, my current Ph.D. And these ones are project students and a master's student, and these two are colleagues. Stefan is currently in Ireland, and I'll go and join him in April for 4 months. So, 13 million people, mostly women, will die in the next 25 years from breast cancer. So this is a very large number, and I'd like to do something about that. The chances of survival are greatly enhanced if you can detect the tumor early, and what we want to do is pass light through the tissue to be able to detect malignant growths associated with, there are two really. Some are associated with the mammary ducts, and some are just there in the blood vessels of the breast. Now, what we have is everything. The breast is predominantly fat. It's got ligaments. It's got a great number of blood vessels. And all of these ducts, all of this structure scatter light. So we handle that in terms of coefficient of scattering. So this is the design for a dual parabola-based volume scanner, and this is what I've been working on for a number of years. So this works by having a rotating prism here, and the light comes along, is focused there. That's the focal point of the parabola. It comes out, it comes through a focus here and goes back. If we rotate this prism, then we can scan around that plane and we illuminate the sample, which sits here, from different angles. We can separate those two parabolas because there's straight lines, there's parallel light in between, so they go through the focus at both ends. And so we have a three-dimensional volume scanner. Here's the equivalent optical train of that, two lens, parallel light in between. We come to a focus. If we've got some scatter here, because it's not at the focus, that then changes the size of the image depending on whether it's before, at the focus, or after the focus. So we've got this measure already that something is different. We can optimize the thickness of this parabola here and the thickness of the section. This parabola must include what we call, it's the old Latin name for it, it's the latus rectum. That plane has the focus of the parabola in it. So provided we've got the focus of the parabola in it, we can use different thicknesses there, and we can model, if you like, the thickness required. Now, stray light is a problem. Human tissue scatters like crazy, and you know this. Next time you go home and you've got a flashlight when there's a brownout, just put your fingers over the flashlight and have a look. It's red, but you can't really resolve the bones. You know you've got some, because you can still move your fingers, but you can't see them. And that's because of the intense scatter in the tissue. So we need to protect our detector from that, and we do that with some appropriate shrouding. So we only look at the light which is getting to the detector. And then we can do things like, in our simulation software, we put an absorber in the middle there, and we can tell if there's an absorber even when we change the scattering coefficient. And I'll have a bit more to say about that in a minute. When we have different lengths of sample, because scattering over here can bounce around, it will keep bouncing until it gets out, basically. And human tissue, even a short volume of human tissue can delay the light by 6 nanoseconds. Now, 6 nanoseconds is quite enough time for a photon to go from your head to your toe to come back again. So it's an extraordinary delay in the tissue. Levi, one of my students, we did a model with, We did a model with an embedded insert here, and we looked at the difference between the scatter without and with, and then we subtracted those two, and lo and behold, we could determine the presence of a scatterer with a very little difference in scattering coefficient. So that we were very excited by, and that has led us to keep working and look at different arrangements with different scatters. We do this with optical modeling software because it's easiest and cheapest to do that, and we can analyze this now in great detail with our rather powerful optical modeling software. But as we'll see later, we have built one of these things. So we can model from different illumination and subtract backgrounds, and again we see the presence of an embedded scatterer. And even when we're a little far away, we still see the presence of that, because scatter you really have to think about when you are analysing the results. So this then is a little movie of us scanning around a sample, and we've got excellent optical performance until we hit that, and then you can see the change that happens on the detector when we've got the scatter and the embedded absorber. So when we have no sample, in theory we have this brilliant, perfect beam. When we've got some sample that has a refractive index, we see, as you would expect, an oblation. When we have a whole lot of scatter and refraction, then we obtain what we expect, a scatter pattern that is oblate. And then if we're a little offset from that, this scatter pattern is an enhanced elliptical pattern. So we have done a series of studies on this, and then we have a prototype. So Ivan Lazate was the first student to put that together, so your UST scholar, and he did really very well. And Marvin Gabriel, Marvin Gabriel continued that work with some different samples. So optical alignment was pretty difficult, but we've got some samples and a piece of apple inside gelatin. Strawberry jelly works best, it would seem. So that was our sample, and we can measure the difference between the scattering of gelatin with position and gelatin and red delicious apple. So if we've got an absorber that's inside, if we've got a 1/4 millimeter diameter copper wire, we can still pick up a difference. Now this is a movie, and I think if you hit it about here, there. Now we live in an imperfect world. If we lived in a perfect world, that red dot would be in the center and it would be perfectly round. Because I'm poor, I couldn't afford the really greatest optics, so we have to deal with that. And this is also a movie, and if we hit that here, please. Yeah, there. This is now with a sample, and what we have is some reflection, but what we did see was a scatter pattern that moved through as we scanned through the apple. So we can optimize this. We can think about light coming in time, and the higher the scattering coefficient, the more difficult it is to get the light through, which is why we don't see very much over here. But we can monitor in our software when the photons arrive, and we see that some of them arrive rather quickly and others arrive rather slowly. You can see that this picture is slowly building up here. So we can discriminate between those. And if there is one thing that has changed in optoelectronics in the last decade, it's detectors. So now you can get time-gated, intensified detectors that makes this sort of thing possible. We can vary the scattering coefficient and monitor the transmission and then plot that, and we've looked at the different size shapes. We have changed our illumination conditions, and this is a movie. So if we just go here, that one should play. And what we have done is scan across an angle here. So we're going from a background, we see highly scattering as we're going through this region here. And then as that one comes to an end, we will form up our central spot again. So things behave as we expect. We have made more complex samples with absorbers. This is work which is going to be presented in June this year at a SPIE conference, where we can determine that changing the scattering coefficient only by 2%, we can detect a measurable difference. Now, what I've shown you up to now is, black screens with little dots on them, and you're thinking, wow, that's good. It's not really, because that is raw information. Now, when you go in, well, I hope you never do, but if you go in for a CT scan, you will have X-rays that come in, and they use a fan of X-rays, and they will go through your human body, and on the other side will be detectors, and they will detect the amplitude of that X-ray beam. And then magic happens. You do a computed tomography, which is why they call it a CT scan, and that inverts that absorption information and gives you an image of your perfectly healthy liver. That's what we need to do. We need to do that with scatter. We need to invert our scatter pattern and come up with some reconstruction that is going to show exactly where our embedded scatterer is. So this is a movie, oops, I beg your pardon, and we'll need to be there, yes. So this is the sort of information that we need to give to a tame mathematician. And that tame mathematician has to say, aha, I know how to invert that data and make that a picture of the inside, ultimately, of the human breast. So that's sort of where we are at present with that. We need to work with our mathematical colleagues to invert this sort of scatter pattern into a real measurable image. So in summary, we need to model the temporal behavior and do this inversion. We need to get better mirrors, and I did get some funding just on Friday for some better mirrors, and optical mammography is still the dream for that work. So that work was supported by the University of Newcastle. So light and its interactions are pervasive. I mean, light and life exists on this planet because of our personal nuclear fusion reactor, which is just 8 light minutes away. We're very happy that it's 8 light minutes away, because if it was closer, we'd get roasted. If it was further away, we would freeze. So we're in this Goldilocks zone, and light remains as a source of wonder, really. And applications of light to human health continue, and we will continue to investigate those and others. There are many others working on that same field. So in closing, I would say that the future is bright and multicolored. So thank you very much.
Thank you very much, Dr. Holdsworth. At this juncture, may we ask both Professor Okamoto and Professor Holdsworth to stay in front and sit in front for our open session. So students, dear faculty, we have the opportunity to ask the questions that have been riddling in your mind for the past few sessions. So if you have a question, we have 2 mics at both aisles. All you need to do is stand up, and you will see my twin brother, Sir Mark, at the back, and he will help facilitate your question. So as soon as you raise your hands, come to the mic and introduce yourself and tell us your question. Who would like to ask first? Sorry, we have one at the back.
That's a very good question. Right now, with our simulation and experiments, we're down around 1/4 millimeter. But the human breast ultimately is, if we said it's 120 or 150 millimeters in diameter, we need to be able to interrogate that structure with millimeter precision. So we would have to try and detect tumors or detect structure that is about 1 millimeter. And we're not close to that yet, okay? But right now, in simulation you can do anything. In simulation, we can detect things about 1/4 millimeter.
Okay, thank you very much. Is there anyone who would like to ask a question? Please raise your hands. And maybe you can stand up. Sir, please. Please introduce yourself.
This young man is a former student of mine from the Ateneo.
Professor Holdsworth, or John Holdsworth, was my physics professor in 1995.
Yeah, I'm impossibly old, as I mentioned earlier.
Anyway, congratulations to Professor Holdsworth and to Professor Okamoto. But my question is for your Japanese visitor. So thank you very much, Professor Okamoto. The issue of HIV/AIDS is very relevant here in the Philippines because of the high, as you said, there's a high incidence of HIV here in the Philippines. And if you are familiar with Dr. Salvana in Manila, he has said that there is an epidemic of HIV here in the Philippines. Now, in one of your earlier slides, you mentioned that one of the challenges in HIV treatment would be the incidence of severe side effects. And I think this is one of the main reasons why HIV patients stop their medication. So I'm not a medical doctor, so I'm just curious, how do physicians address the issue of hypersensitivity to anti-HIV drugs for their patients?
Well, since HIV-infected people have immunodeficiency in most cases, so the incidence of allergic reaction becomes a little lower. But the side effects is usually happening through the inhibition of mitochondrial enzymes that mimics the reverse transcriptase. Okay, so the side effects, the major side effects of reverse transcriptase inhibitors are through the inhibition of mitochondrial regeneration, thus blocking the electron transfer system in the cells, and thus making the individuals with under the treatment of anti-HIV therapy, such as the lactic acidosis that is due to the lack of the electron transfer system. Because of the impairment in normal glycolysis producing ATP, instead of that, they produce the short-chain fatty acids, including lactic acid and butyric acid. That's one of the reasons why the side effects are often occurring. It's not a side effect, it's a kind of efficacy of the anti-reverse transcriptase enzymes. And in terms of the inhibitors for proteases, and most of the physiological enzymes look similar to viral proteases. So those proteases of the physiological relevance are also inhibited, and resulting in the lipodystrophy or lipid alterations in lipid metabolisms, such as high cholesterolemia or hyperlipidemia. And those things usually happens in a month or a couple of months. So therefore, the doctors have to decide to stop it before the patients started complaining the effects of those side effects. Does that answer your question?
Yes. Thank you.
Yep, thank you very much. Is there anyone else who would like to ask a question? You can raise your hand and you can stand up so we can see you. Okay, so we have one at the back. Please introduce yourself.
Thank you for asking that question, because that is one of the points that I didn't go into the details. As I just mentioned to you during my talk, one of the peculiarity of HIV replication is the enormous amplification of gene expression at the level of transcription. And I think, as you may know, transcription, unlike DNA replication, is not 100% proof-read. So therefore, during this augmented transcription, so many heterogeneous mRNAs will be generated, and that will be reverse transcribed into DNA and will become a heterogeneity in the viral genomes in the second generation or maybe third. So that would be considered as the cause of genetic heterogeneity of HIV.
Thank you very much. Anyone else would like to ask a question? Sir, ma'am, please. Okay. So we have one at the back.
I just followed my curiosity. I was just trying to cure the patients with a lot of curiosity. What's going on? That's all.
Thank you very much. Sir, please, go ahead.
I also have a question for my former professor. I was
Thank you. That's a whole 3-hour lecture in itself. But suffice to say that microscopy, the advances in microscopy have revolutionized the imaging which is now possible, and we saw real-time monitoring of a reaction that's taking place between proteins. And this takes place because of the labeling of compounds with fluorescent materials, and I guess there's been a quiet revolution in the availability of the fluorophores, as they're known, and they bind to materials in innocuous ways, so that the central behaviors and reactions of those materials still continue. So it's now possible to look in real time at nerve conduction, the whole gamut of biological reactions that you would want to measure, you can now do so. In terms of resolution, generally, you're limited by the wavelength of light, as you're aware, but last year the Nobel Prizes were awarded for super-resolution microscopy, and these come about with using advanced states of light to suppress the fluorescence from surrounding areas and only leave a little point of fluorescence from the center of a donut, if you like. So that's called STED, microscopy. Two-photon microscopy is something that I've had a lot to do with. My colleague Galia, her thesis was on a new optical scanner for two-photon microscopy, and I could have given that talk here. So there's been a revolution in detection, because the detectors are now absolutely fabulous in comparison to what they were a decade ago, and the techniques that allow you to image in a particular plane, confocal fluorescence microscopy. This has allowed these pathways and passages to be examined like never before.
Thank you very much. Okay, so I think we can accommodate a few more questions. Please, ma'am, introduce yourself.
If I understand your question correctly, you are asking why we are interested in transcriptional step of HIV replication as a weak point.
How did you find out that it is the weak point and not the absorption?
Okay. As I just mentioned in one of the slides, the clinically observed evidences indicating that the higher the virus load, the more rapidly the AIDS develops, suggesting the high viral concentration in the cells, in the blood, is a good indicator of the rapid progression of AIDS from HIV in the HIV-infected people. There is no cause and effect relationship, but it's a strong association between these two independent phenomena. So we supposed that when the virus replication is upregulated, then the cells are being killed more rapidly. Okay? And not only because of that, the action of TAT transactivator that facilitates this virus expression, we found plays a role in suppression of immune deficiency. Okay, so both ways, the rapid viral replication causes the rapid development of AIDS disease. Does that answer your question? Do you have any specific question? No? Thank you for asking.
Okay, thank you very much. Okay, I think we have the fine gentleman at the back.
Yes, I think I explained to you during my talk, but let me just repeat what I have said. I didn't make it very clear at that time. We suppose that those people infected with the drug-resistant clones could have been transmitted from this virus from the patients under the treatment. Okay, so the previous, the person who infected already resistant to the drug, at least the virus, okay? And because of the insufficiency of the treatment, the virus sneaked out of this treatment. Then this virus-resistant clone transmitted to another person, although this person has never been treated by any drugs. In Japan, nearly 10% of those patients were already identified. And probably more such drug resistance clones were found in United States or European countries, although they are naive for any HIV treatment before. So it would happen in this country as well. So we have to treat the patients thoroughly and extensively. Okay, that's one of the lessons that we learned from this epidemiology.
Okay, so I think we can accommodate one last question.
I'm Rex de la Cruz from Applied Physics. This question is for Dr. Holdsworth. So, do you think that there is a much stronger light than the gamma rays? Because black holes emit gamma ray bursts. So I want to know, in the early stages of the universe, is there such a thing that exists that is much stronger than gamma rays?
Yes. So let me expand on yes just a little bit, because I put up the spectrum, and at one end of the spectrum we've got frequencies associated with the delivery of power, and then we sweep through radio frequencies, television, then we get into microwaves, which we use, then we get into near infrared, which we experience as heat. Then we see just that tiny, tiny visible range, and then it's ultraviolet, and then there's X-rays, and then there's gamma rays. Now, if you have an electron positron pair, they will annihilate each other and give off gamma radiation. And you know, that comes about ultimately because of the mass, the mass energy equivalence of those two particles. So you can then go to a proton, antiproton, and even an anti-hydrogen, hydrogen, or an anti-helium, helium, and the energies that they will give off are not that we can readily measure. Our ability to detect light, usually we are transferring that into an electrical signal and measuring the electrical signal. When you have these extreme energies, they just go straight through, and it's very difficult to detect them. What you will ultimately detect, should they interact with something, is you will detect a cascade of electrons. So, you know, to finalize the answer still is yes. Nature is such that there are still mysteries out there, and there are materials and objects and things that we have not yet measured because we don't have the tools to measure them.
Thank you very much. So we can see that many students are interested. I think with the prospect of time, we can ask these students maybe to write your questions and maybe have it forwarded to your teacher so that they can tell them to our professors. At this juncture, let me ask everyone to give our speakers a warm round of applause for a very informative talk. And may we ask our Dean, Assistant Dean, and the Faculty Secretary to please come forward, together with the Department Chairs of Biology and Mathematics, to present our certificate. So our first certificate of appreciation will be for Professor Takashi Okamoto, MD, Ph.D., for having delivered a professional lecture in biology entitled Scientific Explorations in Search for the Genuine Cure for AIDS during the Science Week 2017 celebration with the theme, Science Beyond Borders, Exploring Possibilities, Solving Global Challenges, given this 27th day of February 2017 at the Medicine Auditorium of UST. Signed, Assistant Professor Portia Kitelusi, Ph.D., Overall Chair of the Science Week 2017, Reverend Father Franklin Beltran, Regent of the College of Science, and Professor John Donny Ramos, the Dean of the College of Science. Our second certificate of appreciation is for Professor John L. Holdsworth, Ph.D., for having delivered the professorial lecture in applied physics with the theme, Light and Interactions, also given this 27th day of February 2017 at the Medicine Auditorium of UST. Signed, Assistant Professor Portia Kitelusi, Overall Chair, our Regent, Reverend Father Franklin Beltran, and our Dean, Professor John Donny Ramos. May we ask both of our professors to be in front and to have one round of photo ops. So let's give them all a warm round of applause. Thank you very much. To officially close our present event, may we ask our Assistant Dean, Professor Maria Carlota de Sena, to give the closing remarks.
It is truly a privilege and honor to have in our midst this afternoon two renowned experts in the fields of biomedical and physical sciences. We are grateful to our honorary professors, Dr. Okamoto and Dr. John Holdsworth, for sharing their time and expertise to educate all of us here on the various ways to explore science and make use of knowledge and research findings to address and possibly solve global issues like increasing number of cases of HIV and AIDS, the impact of climate change and environmental change, the increasing number of cases of cancer, particularly that of mentioned by Dr. Holdsworth, which is breast cancer. I remember Professor Cordell in his lecture this morning leaving a message. He said, "Do not stick to what you already know, but work more for what you still need to know." Indeed, this is what we are made to realize from the lectures of Dr. Okamoto and Dr. Holdsworth this afternoon, that doing science is doing research for new knowledge to face the challenges of the changing world. Before we end this afternoon event, I would like to thank all of you who are present this afternoon, despite of today's adversities brought about by the declaration of the National Transport Strike. You made your best efforts to come and be part of this afternoon's activity. Hearing and learning from our honorable speakers was indeed worthy of this time and efforts. Once again, thank you and good afternoon.
Thank you, Dr. Desana. For a few announcements before we officially finish our event, especially to those who would like to ask further questions, Professor Okamoto will be giving another lecture at the College of Public Health in UP Manila on March 2. On March 1, 9 a.m. That's correct. And Professor Holdsworth will also be giving another lecture, supposedly on the blast hole, I think within this week. Tomorrow, I think, February 28th, yes. So Dr. Holdsworth will have another lecture tomorrow at the Blast Hall at 8 a.m. And Professor Okamoto will have another lecture at the UP Manila College of Public Health on March 1, 9 a.m. So with that, may we ask everyone to stand up for the UST hymn.